Hi students, in the last lecture I have discussed what is rolling motion and condition for rolling without slipping. Let us now focus how to calculate kinetic energy and angular momentum in case of rolling motion. Let us see now. So we want to calculate now kinetic energy and angular momentum. So body is rolling without slipping. Suppose velocity of center of mass, it is VCM, and this is now omega. Okay. Assume that it is now rolling on ground. That means for a contact point, velocity is zero, right? Because condition is velocity of contact point should be same as that of contact surface. It is now ground, which has no velocity. So VCM is equal to R omega, right? So we want to calculate now kinetic energy. So rolling means it is a combination of translation and rotation. So when we are taking kinetic energy because of translation and kinetic energy because of rotation about center of mass. So translation of center of mass and rotation about center of mass. So when we are saying translation, for each and every point in the body is having same velocity. So what we are doing is we are replacing entire body with a single point, that is center of mass. So it is now half m VCM square. So this is giving us a kinetic energy because of only translation. Now if we focus only rotation about center of mass, then except the points on axis of rotation, remaining all points are following circular path. So because of rotation, kinetic energy. So this we have discussed earlier, right? In the beginning, half I omega square. And remember, this is I value. This is about the axis passing through center of mass. I am writing as IC, passing to center of mass. Okay. Now in this case, means when body rolling on ground, VCM equal to RMA, right? Then see what we can write. If you want to generalize, means this can be a cylinder, it can be a disc, maybe a solid sphere, or it can be any body. In that case, we are writing I value about its own axis. It is mk square, where k is known as radius of gyration, right? Substitute that value here. And in the place of omega, VCM by R, half m VCM square plus half in the place of IC mk square in the place of omega VCM by R. So VCM square by R square. Now see calculation part, half m VCM square into 1 plus 1 plus k square by R square. K square by R square. So this is now expression for kinetic energy if it is rolling on ground, or you can say for bottommost point velocity is 0. Or let us take k square by R square as some notation here, half m VCM square into 1 plus beta, where beta equal to k square by R square. For example, If you take a solid sphere, for solid sphere, IC value means passing through center, means about any diameter value is 2 by 5 mr square. 2 by 5 mr square. That is equal to m into k square. Now see what's the value of k square by r square? It is a 2 by 5. Okay. How much? 2 by 5. If you take hollow sphere, about any diameter, it is 2 by 3 mr. So by taking about diameter means we are taking axis passing through center of mass about its own axis. Okay. This is equal to mk square. That means in this case, k square by r square, that means beta value is 2 by 3. So now you can guess for ring, it is 1. For disk, it is 1 by 2. Right? Okay. Let us now focus some simple problems. How can they can be asked? For example, as solid sphere is rolling, solid sphere, it is rolling on ground without slipping. Okay. Now find what is the percentage of kinetic energy, that is translation, means kinetic energy because of translation. What is its percentage? Okay. Now see carefully. Half m VCM square into 1 plus beta. When you are taking solid sphere, it is 2 by 5. Okay. This is now kinetic energy because of rolling motion. In this first part, half m VC square into 1. That is because of translation. So because of translation, half m VCM square. Because of rotation, about center of mass, half, here you can see half m VCM square into beta. What is the total energy? Total value. Half m VCM square into 1 plus beta. Now question is percentage of kinetic energy because of translation. Then what we can do here? Kinetic energy because of translation upon total kinetic energy. Then see half m VCM square, half m VCM square gets cancelled. Remaining is now 1 by 1 plus beta. That means see in this case what is answer? Beta value 2 by 5, right? 2 by 5, 1 plus 2 by 5, right? It is a 5 by 7. Okay. This is the fraction of a kinetic energy because of translation. What is the fraction of a kinetic energy because of rotation? Because of rotation. Remaining is now 2 by 7, right? Because total value is 1 fraction. This is a 5 by 7. See one's calculation 1 plus 2 by 5. 5 plus 2, 7. Right? It is a 5 by 7. Remaining is 2 by 7. If they want percentage, then what we have to do? Multiply with 100. Okay. For example, question is that for a hollow sphere, then see what is the answer? Translation upon total value. Translation upon total value 1 by 1 plus beta. What is beta value for hollow sphere? 2 by 3, right? Substitute here 1 plus 2 by 3. 3 plus 2, 5. It is now 3 by 5, right? If you want percentage, multiply on both sides with 100. Then see what we get. It is now 60%. Means for a hollow sphere, 60% will be translation, 40% will be rotation. And remember, this is only when it rolls on ground, or we can say for contact point velocity is 0, then only we can write VCM equal to R omega. So you can see this is a general one. In that general one, we have taken one special case where VCM equal to R omega. Then we got this condition. So while solving problems, we must be very careful. Okay. So like this, they can ask fraction of a kinetic energy because of translation, how much? Because of rotation, how much? Hollow sphere, because of translation, 60%. Because of rotation, 40%. Right? Okay. Let us take to the next possibility. If VCM not equal to R omega, okay, then what happens is we have to focus now this result. Means we are taking separately. Let us see once. Assume that the body is now rolling on a plank which is moving. Okay. Right. Let us see now how to make calculation if VCM not equal to R omega. Right. Let us take a body is rolling. A body is rolling. For example, VCM equal to 6 meter per second and omega. Let us take it as omega value 2 radian per second. Okay. And take radius of this object is 1 meter. Suppose it is a disk. Okay. This is a disk. And let us take mass 2 kg. This is now rolling on a plank which has velocity v equal to 4 meter per second. We can cross check now for contact point velocity. Because of a translation for contact point velocity is now 6 meter per second. Because of rotation for contact point velocity, R is 1 omega 2. So R omega, it is 2. That is now left side. See once. For contact point, because of translation, it is 6. Because of rotation, R omega, it is 2. 6 minus 2, that is 4. And for Planck also velocity 4 only. Means velocity of contact point is same as that of contact surface. So it is now rolling without slipping. So now we want to calculate kinetic energy of that body. So in this case, VCM is not equal to R omega. It's very clear, right? VCM 6 meter per second, R omega is 2. So we cannot take now this result. So we have to take now because of translation how much, because of rotation how much. So kinetic energy is equal to, because of a translation, half m VCM square. Because of rotation, half 5 omega square. So we are taking translation of center of mass, rotation about center of mass. So this is now IC. Axis passing through center of mass. Okay. Now substitute values in this. If you substitute values in this, half mass how much? 2 kg. Half m VCM square 36, right? 6 square plus half. It is now disk about its own axis. Okay. mr square by 2. m r square by 2. Omega square. Omega square means 2 square. It is a 4. Now see what's the value. It is now 36. Plus. So here 2 to 4. 4 gets cancelled. It remaining is 2. Total is now 38. Okay. 38 joule. So like this, we can calculate kinetic energy. Okay. So using this kind of formula is not possible in this case. We have to take separately, right? Okay. Now focus on how to calculate angular moment. Let us see. Calculation of angular momentum. Assume a body is now rolling. This is now VCM. Rotation lines. Rotation may be clockwise, maybe anti-clockwise. Okay. I will discuss both cases. So first we have to focus about which point we are calculating angular momentum, because we are knowing that it depends on about which point r bar cross p bar. So whenever we are taking translation we have to focus L bar is equal to r bar cross p bar. Okay. And when we are taking translation, we are focusing center of mass, because for translatory motion, we can replace entire body with a single point, and that is now center of mass. Okay. Coming to rotation, we focus about which axis body is rotating. So in that case, we are taking I omega bar if body is symmetric about axis of rotation. Okay. Now, angular momentum. This is only because of a translation. So angular momentum because of a translation, angular momentum because of rotation about center of mass. Okay. For example, this is a disk. Okay. And we are calculating about a point on that line. Or let us say this is x-axis. Assume that disk is now rolling on x-axis. Okay. So we are taking about 1 point on x-axis. Now see carefully the position vector of center of mass. The position vector of center of mass. This is r bar, or you can say r bar cm. Okay, because when you are taking because of a translation, we are replacing entire body with a single point. That's why focusing r bar for cm. And if you want only modulus value, now focus. Even though body is rolling, even though position vector of center of mass changing, you can see its a perpendicular distance from x-axis is not changing, right? This is a p bar, this is r bar. Then see this becomes angle between p bar and r bar, right? Then this becomes now perpendicular distance, that is r sine theta, which is a constant, which is equal to radius of that body. That means because of a translation, because of translation, angular momentum is clockwise. See carefully, r bar cross p bar. So take your right hand Keep your fingers of right hand on R bar, curl fingers towards P bar. So because of a translation, angular momentum is clockwise. It is clockwise. Next, because of rotation also, it is clockwise. So both are in the same direction. So we have to add those two. That means it becomes now M VCM into R. This is magnitude, direction part. Suppose if you consider this is X and this is Y. Okay. That means wheel is now, or you can say disk is now in XY plane. Disk is in XY plane. Now angular momentum will be along negative Z axis. See carefully, thumb is now pointing inwards, normal to plane of the board into the board, right? It is minus K cap. Because of rotation, it is again curl fingers, okay? It is now clockwise, curling fingers. Means it is now into the board, minus K cap. So I omega, I value about center of mass, about its own axis. It is mr square by 2 into omega minus K cap, right? For example, the same question, let us take VCM like this, but omega is now like this. In this case, for contact point, velocity is not zero. That means it is now slipping. See carefully here. Because of translation, velocity, VCM right side. Because of rotation, again for contact point, velocity right side. That means it is now rolling with the slipping. Okay. And we want to calculate about a point. If this is x-axis, about a point, what is angular momentum? Only changes you can see because of a translation, it is again minus k cap direction part. L bar m into VCM into R into minus k cap. No change in this. But coming to rotation, it is now anti-clockwise. So thumb is now outwards, right? If you curl fingers of your right hand anti-clockwise, thumb is pointing outwards. Means it is along positive Z axis. It is a disk now, so mr square by 2 about its own axis, mr square by 2 omega, it is a k cap. So simply focusing because of a translation what is value, because of rotation what is value, then taking the vectors. So mainly we have to focus about which point we are calculating. Okay. So I hope you got a clarity.